Okay, for this next segment, I want to introduce the chi-square probability distribution, show how to set it up, and then I will apply what we know now about our the hypothesis we've been working with, sex and poverty. I will apply that to the probability distribution and make a decision whether or not to accept or reject the null hypothesis. First, this is a picture of the chi-square probability distribution. If you're thinking to yourself, gosh, that looks pretty close to the F probability distribution, you are right on the money. It is only one-sided. There is no such thing as a left side. There are no such thing as negative chi-square values. So here you have it. That's how you draw the picture, very much like the F probability distribution. And when you think about it, there's only one side to the distribution for the same reason that there's only one side to the F probability distribution. What does the F probability distribution measure? Between group variance. Well, there's either variance between the groups or there's not. Another way of looking at variance is difference. That's what chi-square measures, difference, right? Things either differ, right? A value falls somewhere on here indicating a difference between observed and expected frequencies, or they do not differ. There's no such thing as negative difference. In fact, the chi-square formula, if conducted correctly, and if all the math that goes into it is done correctly, the chi-square value will not allow for negative numbers. All right, so if you're doing chi-square analysis and you came up with a negative number for data-generated chi-square, something went wrong along the way. This is a picture of the chi-square probability distribution. It is one-sided. It has a body. It has a tail. Next slide. Taking this step by step. If you are asked to solve problems using chi-square analysis, you should produce a drawing that looks like this. Same sort of shape, right? A one-sided shape, indication of a tail. I put the question marks here because we don't know, we haven't done an example yet. If you were told to test a hypothesis at the 0.05 level, this tail would be 0.05. This part then would be 0.95. Why? How did we know that? Because the whole thing together has to equal 1. If you were asked to test a hypothesis at the 0.01 level, this portion, this tail would be 0.01. This would be 0.99. If you were asked to test a hypothesis at the 0.10 level, this piece would be 0.10. This piece would be 0.90. If you were asked to test a hypothesis at the 0.001 level, this piece would be 0.001. This piece would be 0.999. Up here you have the legend, degrees of freedom. Do you remember how to calculate the degrees of freedom? Number of rows minus 1 times number of columns minus 1. And then you would also place the alpha level. Although the alpha level is redundant, it's also expressed here, but you should put it here as well. Degrees of freedom and alpha level. So let's say you were asked to test the hypothesis. This hypothesis, sex is not related to poverty, right? That's what we've been working with since we introduced hypotheses, right? Carrying this through. Let's say you were asked to test that hypothesis at the 0.01 level. 0.05 level. You were asked to test that hypothesis at the 0.05 level. This is what the drawing would look like. You were asked to test the hypothesis at the 0.05 level, so we drew the picture. This size is 0.05. This size is 0.9. This piece is 0.95. Degrees of freedom are 1 because we're doing a 2x2 contingency table, right? Sex, male, female, poverty, at or below versus above the poverty line. Okay? So a 2x2 contingency table, 2 rows, 2 columns, 2 minus 1 times 2 minus 1, or 1 times 1 is 1. So degrees of freedom is 1 for a 2x2 contingency table. The alpha level is 0.05. And then I consulted the chi-square probability distribution right here. 1 degree of freedom, 1 degree of freedom at the 0.05 level, 3.84. And that's what I put, excuse me, on this drawing. 3.84. Testing the hypothesis at the 0.05 level, 1 degree of freedom, tabled chi-square value of 3.84. That number, 3.84, it came from the table. That is the tabled chi-square value. That is the, and this is very important language to understand, that is the maximum amount of difference between observed and expected frequencies that we could expect to occur by chance alone, given these conditions, given 1 degree of freedom, a 2x2 contingency table, and an alpha level of 0.05. That came from the table. 3.84. That is the maximum amount of difference between observed and expected frequencies that we could expect to occur by chance or sampling error alone, up to, but not exceeding 3.84. Well, how much did we observe? Well, if you recall from our previous YouTube clips and previous calculations, we observe our data generated chi-square value is 2.564. That's how much actual difference we observed between the observed and expected frequencies. That's what we observed. So let's apply this to the drawing. Same stuff. Null hypothesis, sex and poverty are unrelated. Test that at the 0.05 level. 0.05, 0.95. Tabled chi-square value 3.84. So this is all the same from the previous handout that I just showed you. Except here I placed where the data generated chi-square value would be, 2.564. 2.564 falls somewhere in the body. It does not exceed. It was not greater than 3.84. Therefore, we retain or keep the null hypothesis of no relationship. And in fact, I'll read the conclusion right here after setting it all up appropriately. The amount of difference between observed and expected frequencies could reasonably be attributed to chance or sampling error alone. And then I state definitively, relate it back to the hypothesis, which I've been encouraging you to do. Sex is not related to poverty. That's what we can conclude. The amount of difference, again, this is the conclusion, this is how I would write this up. The amount of difference between observed and expected frequencies could reasonably be attributed to chance or sampling error alone. Sex is not related to poverty. Now, if our calculations indicated a greater amount, if our data generated chi-square value exceeded 3.84 and fell here in the tail, in the rejection region, we would not retain or keep the null hypothesis. We would reject the null hypothesis, and we would say instead that the amount of difference between observed and expected frequencies cannot be, we observe more than can reasonably be attributed to chance alone. And so therefore we reject the null hypothesis of no relationship. It appears that the two things would be related. But in this case, we did not observe an amount of difference between observed and expected that was greater than what we could expect to occur by chance alone. Therefore, those two things are independent of one another. They are not related. And so that is a chi-square example from cradle to grave.